Yes.
Okay. So we shall, for those who missed out last time, I will do a very brief recap, and then we shall understand more what digital electronics is all about. It is a very interesting topic and a simple one to comprehend. So I just pray that you pay extra attention. Now I'll begin with a question. I won't ask that how many of you have gates at home, but I'll just ask. I know that many of us, where we study from our schools, we have school gates, not so? Some schools have got one gate, others they have got two gates and etc. But my question will be very simple. We had a class captain last time. She was doing a very great job. I don't know if she has joined. I don't know the name. Class captain, have you joined?
Maybe she's coming.
Okay, she'll join us. Okay, yes. So I will ask a question. What do you think is the importance of a school gate?
School gate. First of all, it provides protection.
That's one.
Security in the school.
Okay. You are saying that it provides security, that's two. I need some more two, and then we relate.
We have your one Callista. He has the answer. We request you to unmute him. Maybe he has an answer. I'm seeing his hand up. And Muwau.
Callista and Muwau.
They are muted.
Okay. I'm trying to share a screen here. Okay. Please go ahead and tell me. Muwau, they are muted. Okay, let us just go by what the other two people said, that for security, they allow people to come in and move out. Opening and closing of the gate is a way of saying that you are free to come in or you are not allowed to come in. Now, to relate with that, the switch acts as a gate as far as a circuit is concerned. So if you have any of your circuit, then a switch acts as the gate, and that switch, its major work is to allow current flow or not allowing current to flow. Is that okay? So in case you are stuck, you let me know. So for any circuit that has a battery and then a switch with it, a switch plays a very vital role. We have said that it is either on or off. The two conditions give two possibilities that either current is flowing or current is not flowing. Can someone tell us, when the switch is on, is current flowing or not? I think that is obvious. Current is flowing. And when the switch is off, then current is what? Current is not flowing. Sometimes we use open for off, and sometimes we use closed for what? for on, not so? So we shall see that under this section, we shall be using uh, two antagonistic words. The word antagonistic means that one is exactly the opposite of the other. Something is either on or off. So, or something is either high or low, or something is either true or false. So those two cases that are opposite to each other, we shall be guided by them. Is that okay? So as we progress in this kind of chapter or topic, we shall learn something very interesting, and that's where the word logic comes in. A switch is a gate. We said that we relate to the school gate. Allow me to first, because these people have started where they stopped, disable annotation. Thank God today I've realized it a bit earlier so that these people who write in our work don't disturb us. I think we have immunized them. Okay. So I'm saying that there are two cases. That is on can be closed, off can be open. It can be high or low, where high can mean on or low can be off, depending on which circumstance that you are dealing with. Is that okay? Now, when we relate with digital electronics, I was mentioning something very interesting, that we use the word logic in this case to refer to this kind of gates. It has only two ways, on and off, like we shall see. But these two ways can perform millions of tasks. In their simpler way, they can perform millions of what? Millions of tasks. So because we have only two options, we assign, if we are to assign numbers, then we shall have only two options. The two numbers can be a 0 or a 1. Is that okay? So a 0 or a 1, where a 0 can represent low, 0 can represent off, 0 can represent open. Then 1 can represent on, 1 can represent closed, 1 can represent high. Now, any question? Yes? Okay. Someone is putting up their hand. I don't know who is going to guide us in unmuting them so that they can ask. But like I said, since we don't have a lot of time, I think you have provision to ask, don't you?
Teacher,
Yes?
you are the one who is supposed to unmute these people. Maybe. Because here we are unable to unmute ourselves.
But for you can talk. How come?
I don't know. For me, maybe you have unmuted me because at first I was muted.
Okay. Okay. So did you have a question?
No, I was just raising that concern.
Okay. So I think I've unmuted Jonathan. Jonathan, do you have a question?
Yes, master.
Mm.
My question is,
Mm.
I would like to know where digital electronics is applied in real life.
Don't worry. We are just beginning.
We are just starting the topic.
We are
Uh,
on an
I thought,
introduction.
I
We
thought
shall
that
see.
started last time.
No, we are having a recap. I know some of you missed out. So we are rushing through a recap, and then we shall have the daily life applications. Is that
Okay,
okay?
master. Yes.
So I'm saying that just like a school gate, a switch can act as a gate to a circuit, where the two possibilities can be a 0 or a 1. That is if you have only one switch. Meaning that if I have one switch, the only two possibilities are it can either be off or on. Or, yeah, it can either be off or on. That is the 0 and a 1. So this kind of computing or this kind of system is referred to as a binary system. You remember binary base in senior 1? where digits are converted into 0 and 1, where all bases, whichever you type in a computer, it is changed into a binary base. Is that okay? So digital devices, digital computers, their capacity is to work out, to do computations in only 0 and 1. So now, because a switch acts as an opening for a circuit to allow current in and to allow current out, there are two major conditions that we can consider. I think let me first share a whiteboard, because I need to first explain most of these things. Then I will share our work. So let me see. Where is the whiteboard? Checking for whiteboard. Okay, so then we need to go back and then I look for this whiteboard. Okay, so I'm saying that we have looked at a very simple circuit. A very simple circuit is one that has, number one, it has a switch. It has, okay, let's say there is a bulb, because a bulb can show us results. You can't see current with your eyes, but you can tell that current is actually what? Current is flowing. Is that okay? When the bulb is lighting or when it is not lighting. So if this is our switch, I think we had done something so that people don't interfere with our screen. I don't know what happened, how this one came to start writing. Let me look for that option. Okay. If I'm not seeing that option that blocks people from writing, I'll go back to the screen, because when I share screen, that option is there where people can't write unnecessarily. Sorry, I'm looking for sharing the screen. The subject is digital, the chapter is digital electronics. It is in physics, the last chapter in physics. The last chapter in what?
Physics.
The last chapter in physics. So I want to share a screen so that these people who have nothing to do, they don't disturb us. Okay. Yeah, I think with a screen, they cannot. So we can continue. Eh? Okay, so I said that where you have a simple circuit, connect to a bulb, and then connect to a what? a battery. And this should be a complete circuit. Don't leave these open wires where wire does not reach a certain point. So we have a switch, let's say K, and then we have a bulb, and we have a battery with voltage V. Now the question is, a switch has only two conditions. It has open, and also it has what?
Close.
It has closed or close. Then this side we shall have the result. For those who were here last time, we went through this. I'm going through briefly. So when the switch is open, we give it a 0. When it is closed, we give it a 1 because we are working in binary digits, not so?
Yes.
So result, what shall we obtain when the switch is open? When the switch is open,
the bulb will give out light.
The bulb will be off, and when it is closed,
It
the
will be
bulb
on.
will be on, not so?
Yes.
Okay, now let's go to something very interesting. That is supposing you have two switches. Supposing we have two switches, and then this is our that's our battery and that's our bulb. Then we have switch 1, switch 2. Take note, because we don't have a lot of time. I said that every time I mention 0, it means the switch is open. Every time I mention 1, it means the switch is closed. Is that okay? So if I say 0, in your mind, you should know that the switch is open. If I say 0, it is open. If I say 0 when K1 is open, then 1 when K2 is closed. 1 when K1 is, we are looking at the different possibilities. 1 when K1 is closed, 0 when K2 is open, and 1 when both are open. Is that okay?
Yes.
So on the other side, I can write the result. Now, still under the result, I will say 1 represent on and 0 represent off. Now I mean the bulb. Is that okay? So what happens when K1 and K2 are both open? 0, 0 means both are open. The bulb will be off, and off can be represented by a 0.
0.
I hope people are following.
Yes.
When K1 is open, that's a 0, and K2 is closed, what do you think is going to happen? That's a series arrangement. What is going to happen?
The bulb will give light.
Are you sure? Okay, let me get one serious person. I make her or him a co-host so that he can help me with those who are putting up their hands to unmute them. One serious person. Of course, all of you are very serious. But remember, we have those few who came to disorganize us, those who keep writing in our screen. So I'm just making one of you the subject, not the subject. Now the brain is mathematics. The co-host. So on Subuga, you can guide those who want to give answers or to ask questions. Okay.
Okay, sir.
So what happens if K1 is closed? If K1 is open and K1 is closed, remember, by this time, I assume that you learned electricity. So if you learned electricity, and one of the switches is open, do you think the circuit is going to be complete?
Samantha should tell us.
There won't be light given by the bulb due to the what? Voltage won't be flowing through, passing to the bulb.
Yes, so that means that we shall have a 0.
Yeah, a 0.
And so we have a 0 for the second case, because for as long as one switch is open, the circuit is not complete. So we have a 1 when both switches are closed. Is that okay?
Yes.
So now how do we draw a conclusion from that table? Pay attention to this. The conclusion from this table is that for current to flow, both K1 and K2 must be closed. Both K1 and K2 must be closed. Underline the word and that's how we come up with another gate. Remember, who remembers the first gate? First gate was when you have just one switch in a circuit. That switch acts as a gate. Now, when you have both switches, they create a combination, and that combination now is called the AND gate. So AND is a combination of two switches. In this case, these switches are connected in what? The switches are connected in series. Do you see that?
Yes.
So we arrive to this gate by the fact that the circuit is only true if both if K1 and K2 are closed. And that's the origin of the AND gate. AND gate is a combination of two gates, the K1 and K2. But these two gates are arranged in series. Is that okay?
Yes.
To pick a leaf from probability, just picking a leaf, I'm not saying that they are exactly the same, but to pick a leaf, and is represented by a multiplication. When I say A and B, it's the same as saying A times B. A times what? A times B.
B.
Take note of that. Is that okay?
Yes.
Okay. So because of that, now using the knowledge of the AND gate that we have just learned, AND gate, which is a combination of two gates, and a gate is simply a switch. The combination of two gates is that if our switches or gates K1 and K2 are arranged in series, then the knowledge of AND can give us the result as follows. If this is my table, by the way, the table in which we generate all these results is called a truth table. Remember, I told you there are two options in digital electronics. There is either 0 or 1. There is either high or low. There is either true or false. So a table is called a truth table because if something is either true or false, so we call it a truth what? A truth table. So I can say K1, and we are using capital letters for this case, K1 and K2. So the possibilities are they can either both be open, or this is open and this is closed, or this is closed and this is open, or both of them are closed. And based on what I said, that we can treat AND as multiplication, let us see if that gives us the same result as the one that we saw before. K1 and K2, it means I'll be multiplying K1 times K2. 0 times 0, you get a 0. 0 times 1, you get a 0. 1 times 0, you get a 0. 1 times 1, you get a 1. So, meaning that the AND gives us the same result as one we obtained earlier when we connected the circuit and the switches in series. Do you relate?
Yes.
Okay,
Erima wants to say something.
Let me first pause for a minute in case there is any question.
Erima? And Hannah,
Mm.
Erima and Anna.
Teacher,
Yes.
you said that this is the AND gate, but
Mm.
then could you please pardon on the first gate, the OR gate?
Have I said anything like or get?
You haven't.
Another one.
Then Sekaita Emmanuel.
Okay, maybe to answer her question, she's asking, how about the first gate that I talked about? The first gate where we have only one switch, maybe we have a bulb. This one doesn't have any name. It is simply the simplest gate. In other words, just one switch. Just
Yes.
one what? Just one switch. So it is just a gate. Is that okay? Because
Then
a switch,
Sekaita Emmanuel has a
or
question.
an opening to the circuit is simply a gate. Is that
Yes.
okay?
Okay. Yes. Okay, yeah. Like I wanted to know if for AND gate to be true. No, for AND gate to be working, the two possibilities, K1 and K2, should be true for us to have the output to be one. Both the inputs should be one. Is that right? Or
Yes,
there
you are
is
true.
something?
You are true.
Okay, thank you, sir.
Okay. Okay, so from this step, I said this table is called a truth table, not so? So we can now write this one, the symbol, we just write it.
Yes.
We've said that now what we are looking at so far is called the AND gate, which is the combination of two gates. And these gates, practically, they are switches that are connected in series. Someone was asking, what is the day life application of what we are looking at? So these are switches connected in series. And we've realized that current can only flow if both are closed. So the symbol for this kind of gate is that, yeah? Where this is our K1 and that can be our K2. And then the output is K1. We said the output is K1 and K2. Is that okay? Yes, Michael.
No, for me, I'm just a co-host, but my hand. Let me know.
Okay. Okay, people, please, in case you are not asking a question, make you leave the hand low. I hope we have understood the AND gate.
Yes.
And now, because let me just give a day life application of this AND gate. Yeah. Say for example, a school has two gates.
Yes.
A school has two gates. Just pay attention to this. A school has two gates. Let me say gate 1 and gate 2. And the school is only safe if both gates are closed. Let's assume there are no guards at the gates. And we are saying that if the gates are open, the school is not safe. If one of them is open, the school is not safe. So the school will only be safe if both gates are open. So whichever the first conditions that maybe both are open, of course, when both are open, the school is not safe. When one of them is open, the school is still not safe. It is only safe if both gates are closed. So this kind of arrangement is the daily life application of the AND gate, and we shall see, we shall modify it a bit to put conditions like if one of the gates is open, maybe we've designed a digital alarm system that makes an alarm when one of them is open. So we shall look at that. We shall reach at that. But for now, we know that daily life application of this kind of AND gate, if we slightly move away from the circuit things, then it can be the gates, the gates for the school. Is that okay?
Chamber has a question.
Mm.
Let me unmute you. Chamber, you are unmuted.
Good afternoon, teacher.
Yes.
And yes, I just wanted to bring your explanation in a different way, if it's okay with you. Let's say, for example, that school has two gates that are collinear. They follow each other. So if one gate is open, that means no vehicles are allowed to enter, right? In this case, that is one switch. Now, if both gates are open, that means vehicles can go in and they can go out. That is the second switch. So in this case, that's the AND gate, right? Yeah, that's my explanation. I don't know if it has helped anyone.
It makes sense.
Excuse me, teacher. Excuse me, teacher. Even for
Yes,
us at
please.
our school, they gave us an explanation about the AND gate that for one to go abroad, you need a passport and a visa. So if you have a passport and you don't have a visa, you will need to go. If you have a visa and you don't have a passport, you will not go still. But if you have a visa and a passport, then you can go.
That's a good one. Let us try to figure it out in a truth table. Passport, with the passport, 1, no visa, 0. No passport, yes. 0, visa, 1.
Yes.
No passport,
you have...
no. No passport, no visa, and then there is a passport and a passport. So what is going to be the result? So the possibilities are, with AND we just multiply, and the answer we get can explain what he has talked about. When we multiply, we get 0, 0, 0, and 1. So the result explains that you can only go abroad only if you have a passport and a visa, which is very true. Is that okay?
Yes.
Okay. Now this is for the two inputs. This is for the two inputs. Maybe here passport and visa, and then the result or the output P and V. Now, let us just extend it a little bit. Supposing we have three switches. Three switches, or supposing we have three inputs. Let's just extend our circuit a little bit. Now we have another switch. Let's call it K3. Then our truth table will be K1, K2, K3. Okay. We shall have, then here we shall have our result. We shall get, let us just use this circuit for now. So how many possibilities do we have now? If there are three switches, when there were two switches, we had how many possibilities?
2.
1, 1, 1, 0, 0, 1. We had 4 possibilities. Yes. So if the switches are 3, we are going to have 80 possibilities. So switch 1 They can all be open. You see that? Or one can be open, two open, this one is closed. Or this one open, this one closed, by this one. Okay, let me repeat myself. They can all be closed, or one closed, closed, open, or closed, open, open, or closed, open, open, or closed. Tell me. Closed, open, closed. Have I done? Let me repeat that one. Closed. No, this is open, sorry. Open, closed. Which other possibility? Open, closed, open, and then the last one is when all of them are open. So how many possibilities are those? These are 7. They should be 8. Which one have I skipped out? Let us repeat.
There is someone. Zoom user on. What is your question?
Both of them are closed. Closed, closed, open, closed, open, closed, open, closed, closed, open, open, closed. Tell me another possibility. Closed.
Closed. Closed.
1. There should be another. There should be 8. So far, these are 6.
Open. Open. Open.
There should be another one.
Then let us give a chance to someone here. Queen. Queen. Unmute yourself.
Okay. First, school how to get all the options. So in this case, there are 3, so we have to total up. Then we go on adding 1. So in the first place, if we have 0, 0, 0, then we add 1 in the place of K3, meaning the second option is going to be 0, 0, 1. So then you add another 1 at the end, but since it's binary based, 1 plus 1 gives you 2, and it doesn't fit in binary base. So you're going to get the third option as 0, 1, 0. Then when you go on adding 1, you get 0, 1, 1. Then the next option, 1, 0, 0. You add on 1 again, 1, 0, 1. Add on 1, you get 1, 1, 0. Then finally 1, 1, 1.
So what are we missing?
Then bracing rows.
I just want someone to tell me what we are missing. Yeah, she's giving an alternative. I have also a simpler one, but someone you can tell us what we are missing.
Blessing rows.
Teacher, you repeated 1 gate. You have 1 1 in the first place, then also the second last is also 1 1.
Now we are missing 2.
Shadrach is saying that 0, 1, 0.
0, 1, 0.
Then
another one.
I say 1, 0, 0.
Wow, 1, 0, 0. Like that, yeah?
Yes.
Okay, there is another way I'm going to share with you, a simpler way, because you may not keep guessing, yeah? You may not keep guessing. So, how about the result? Now let us go to our circuit and we relate. If all the switches are closed, current will flow. The bulb will be on. If the bulb is on, that's a 1. So what is the result for the rest? For as long as one switch is open, what does it imply? No current is going to flow. Do you understand that? All together? Are we together, friends?
Yes, Alovic has something to say. Alovic, please unmute yourself. Maybe he's not ready. Faith.
Okay. So this result can also be obtained using the AND gate result. And we see that if we simply multiply everything, the first row will give us a 1, and then the rest will give us a what? The rest will give us 0, 0, 0. So in other words, still we are operating on the AND gate system. Like I said, there is another simpler way. She mentioned a way to get that when they are 3. Yeah, but we can have another one, another simpler way, so that you don't have to keep guessing, yet we don't have time. So another simpler way is to first treat the first 2. You remember how we do the first 2? 1, 0, 0, 1. Or it can be 1, 0 or 0, 1 or 0, 0 or 1, 0. Then I repeat the pattern. I began with 1, 0, then next was 0, 1, and then 0, 0, and then 0, 0, and what? I think this was a mistake. This was supposed to be, okay. That was supposed to be a 1. Is that okay? Now we treat these 2 as AND, K1 and K2. They are AND, and if they are AND, we can have another one as 1, 0, 1, 0, 1, 0. No, I think it's the other way around. 0, 1, 0, 1, 0, 1, 0, 1. Is it? Okay, I think we are going to check it again. We are going to check it again using a logic circuit diagram. Using a logic circuit what? Diagram. Okay, that one we are going to check it again. There is another way where we first combine 2 and then we come up with a third one. We shall check it again. So for now, let us now go to the to another circuit, that is the parallel arrangement. Parallel arrangement of 2 switches. Let's say we have a switch where we have a circuit in which we have 2 switches arranged in what? I'm trying to be a little bit faster because we looked at this one last time. We're just revising. Yeah? For those who missed out, pay attention. If this is my battery, and that is my bulb, if we call this one our switch K1 and call that one our switch K2, K2. If I have this one as my K1, I have this one as my K2. And then here I have my result. I have my result. So we begin with the two switches still, K1 and K2. What happens if K1 is, remember the possibilities, it is either open and this one open, or this can be open, this one closed, or this one closed, this one open, or both of them are closed. So what is the result? If I close, if both are open, someone tell us what is going to be the result with a bulb. Remember, with a bulb, it can either be on or off. That is the result we are talking about.
Mary Shift has something to say. Yes, Mary.
If both switches are open, the bulb will be off. But
and
I
off is
also have a
represented
question.
by
Like, teacher, what did you base on, like, to know the number of patterns? Because you said in the other one for 3 switches, you say the number of patterns, they have to be 8. What did you base on?
the number of combinations.
Yes.
Oh, you know, when they are two, we identify the possible combinations. The combinations are, there is a possibility that both are open. There is a possibility that one is closed, one is open. There is a possibility that the first one is open, the second one is closed. There is a possibility that both of them are closed. So I don't guess the number of times or the patterns. It comes automatically that if there are 2 switches, then there are 4 possibilities. Is it okay? There are 4 possibilities. Now, if there are 3 switches, you realize that if there are 3 switches, then the possibilities can be that both of all the 3 are open. You see that? Or you may find that only 2 are open, but the third one, K3, is closed. Or you might find out that the first one is open, the second one is closed, but the third one is open. Or you may find out that the first one is open. No, the first one is closed. The second one is open. And the third one is what? Is open as well. Remember, I'm not intending to repeat any pattern that I said before. Or there is a possibility that the first one is closed. The second one is what?
Opio Livingstone.
Second one is open, and the third one is what? Closed. So there is a possibility of having the first one closed, the second one open, and the third one what? Yes?
Mr. John.
Yes?
To make them understand better. For these 3 switches, when you have the 3 switches, remember we are dealing with binary bases. So now, where there is K3, you're going to put it 2 power 0, and the result is going to give you 1. Then in K2 here, they will put 2 power 2, which is going to give them 4. Then where there is K1, they put 2 power 3, then they will be in position, because here we have 2 power 0 is 1, then 2 power 1 is 2, sorry. 2 power 0 will be 1, then 2 power 1 will be 2, then 2 power 2 will be 4. Now, when a person is writing for K1, you can start with, because now we have K1, we have 4, K2, we have 2, then K3, we have 1. So,
are you writing?
And now when you're writing, let me first check whether it's accepted. I'm not accessing the pencil.
Okay, let me first stop sharing, then you can share.
So let me open this. Don't disturb. Now when we have these switches, we are going to have our switches at this point. They are going to be 3, whereby the first switch we were calling it K1. The second switch we're calling it K2. Then the third switch, this one we were calling it K2. Sorry. Let me remove here. We had the first switch. Guys, don't disturb. First wait. We had the first switch to be K1. We had the first switch to be K1. The second switch we had it to be K2. The third switch we had to be K3. Now to get the possibilities you're going to write here, we are dealing with binary base and there are 3 switches, which means when you're dealing with binary base, here we are going to have two in K3, you're going to have 2 power 0, which is going to give you 1. Then in K2, you're going to have 2 power 1, which is going to give you 2. Then in K1, we are going to have 2 power 2, which is going to give you 4. Now this 4 means you can start by writing the first 4 zeros, then you end with the last 4 ones. Or you can start with the first 4 ones, then you end with ending 4 zeros. So when we start with 0, you shall put 0. We shall put a 0 here, a 0, not until you make them to become 4. Then after the 0, you can now write now the 1s also. We are remaining with 4 ones. You write now 1s also, not until they become 4. You write 1 also. You have 1, 1, 1, 1, not until they become 4. Now here, for K2, where we had 2 power 1, which is 2, we started with zeros, which means first write the first 2 zeros. After the first 2 zeros, come to the first 2 ones, like that. You keep on alternating. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, like the way he's writing. Then in 2 power
2 power 0 is a 1. So you write 0, 1, 0, 1, 0, 1, 0, 1. Is it what you are saying?
0, which is giving you 1. Since we are starting with a 1, so you build the next 2 zeros like that. That is the way can be the simple simplest way for them to understand. I don't know whether I've made them to understand those that were writing that they are confused. Are we together?
Yes, we are together.
Yes,
Have we understood?
We have understood, but there is someone who is saying that he has another alternative. Please raise your hand. I've seen the gun in the chat. Conqueror. Raise your hand, please.
Okay, you can stop sharing, Mr. Pio.
Okay.
Whoever has an alternative, you can say it if possible, because someone is doing us a disservice. So we shall keep. Maybe you can let me know in case I get what you want to say. I'll write it so that people don't disturb us. Yeah.
Fisher Conqueror.
Yes, please.
Conqueror.
The method
Yes,
I
Conqueror.
had is almost the one that Apia just explained, whereby you first write the zeros in the K1, you write 4 zeros, followed by 1. Then in the second one, you write 2 zeros, 2 1 1 till the table gets full to 8 digits. Then in the last one, you write 0 1 0 1 0 1. Then the table will be complete with the right values.
Yeah. Okay.
Then bless you.
Okay, those are enough. We need to go to the other gate, yeah? At least this one is very simple because they are saying that the first one is to the binary base to the power 0, 2 to the power 1, and then this is 2 to the power 2. 2 to the power 2 will give you a what? Will give you a 4. This will give you a 2, and this will give you a 1. So the 4 means that I'll have all the 4 zeros first, and then the 1 next, like that. Then the 2 power 1, which is a 2, the pattern will repeat after every 2 digits. 0 0 1 1 0 0 1 1. And then the 2 power 0, which is a 1, it means the pattern repeat after every 1 digit. That is, if I begin with 0 1 0 1 0 1 0 1. I think that is simpler for all of us to get, yeah.
Yes.
So that is when they are three, or when they are three gates. And then our symbol becomes K1, K2, and K3. So then our output can be K1 and K2 and K3. That okay? Okay, now let's go back to thank you so much, Mr. Pio. Let's go back to, we are looking at the parallel arrangement. Where if we have K1, we have K2, and then we have our bulb. And then the battery. So we are looking at the two possibilities, K1, K2.
I have a question. So, Master, why are we dealing in the binary base?
Why are we dealing in the
binary base?
Okay. So maybe another person will add on, but I can say something. The kind of signals that we are used to, even when you speak, the kind of wave or the kind of signal that you utter out is an analog signal. So the computer is designed in such a way that instead of having an analog signal is one that can be represented by a sine wave, a continuous signal whose wave is represented as that. So there is another way that a computer or other gadgets are designed. They are designed that instead of having that continuous signal, they can have only two possibilities. They are designed in such a way that their possibility of operation is either a 0 or a 1. That if something is in a 0, then it can the computer interprets that is 0 in the way that it is designed to. So whereas we have information kept in line with analog signal, analog now I mean these continuous waves, that digital circuits are designed in such a way that they operate only in 0 and 1. And 0 and 1, when we go to the knowledge of bases, that's a binary base, because base 2 is where you have only two possibilities. That's a 0 and a 1. Is that okay? So the design of these digital devices is in such a way that they operate only in two possibilities, a 0 and a 1. And that's why they are called digital devices. And their operation is called a binary what? A binary operation.
To add on him, when we are dealing with the binary number system, the rest of the binary systems follow first of all, they originate from the binary system. When you go to base 3, base 4, all they are originating from the binary system, right? Now, when you say why we are dealing, that one who is saying why we are dealing with binary base is, binary base is the origin. I either have something or I don't have, right? So I cannot bypass 2 when I have not passed 1, right? So for example, when you need the light, you either have light or you don't have light. One of those things. So not having is what we're saying is 0. Then having can be a 1, that possibility we have a 1. Like when we are dealing with probability, you either have or you don't have. So that's why we are dealing mostly with binary base. The other bases, they are all originating from the binary number system. So we take the first binary number system, leave alone the other ones, because it is the first in bases when you are dealing with bases.
Okay, thank you. After all the other numbers can be converted to binary base. You can convert any number back to binary base. Okay. Thank you so much. We can move a little bit faster. So with this parallel arrangement, we are saying that when K1 is closed, K2 open, or can we use the knowledge that we've just learned? Say that they're in base 2, so this can be 2 power 0, and this can be 2 power 1. 2 power 1 is the same as 2. 2 power 0 is the same as 1. So the 2 power 1, which is a 2, means the pattern repeat after 2 digits. So it can be 0, 0, then 1, 1. And then the 2 power 1, which is a 1, it means this can be a 0, 1, a 0, 1. Is that okay? That the pattern repeats after a single digit, but here after two digits. I think that method is easier for all of us, yeah? Is that okay?
Yes.
That even if there are 4, now you know what to do. So what is the result? This result, before we go into the, before we conclude which gate we are dealing with, let us just take, for instance, this, the table. I mean the circuit. And in the circuit, if you close K1, current will remain flowing through K2. Now, if both of them are open, current will not flow. But if one of them is closed, then current will do what? Current will flow, even if both of them are closed. Now listen to this. How do we interpret this? We say that current will flow either one of the switches is closed or both are closed. And that is the origin of the OR gate. So either both switches are closed or one of them is closed. Current will flow. And that's the origin of the OR gate. Is that okay?
Yes.
So what is the symbol for the OR gate? We have something like that. We have, yeah, that is our OR gate, where this is the inputs K1 and K2, and then the output is K1 or K2. That is our output. Is that okay?
Teacher.
Hmm?
Excuse me, sir. I thought that for the case of the OR gate, at its end is quite sharp, not like that one is growing. There where the outputs are.
Like that, like this one.
Yeah.
It's okay, either way. What we emphasize is the curving here. This curving, yeah?
Okay.
Is that okay?
Yes.
Okay. Now, do you remember the kind of mathematics that maybe, or when we borrow the knowledge of probability, or means what?
Excuse me, I have a question.
Yes.
The number of rows, sorry. How determine the number of rows?
Which
like
rows?
In K1 going down. How do you determine, like, how do you know that here they are supposed to be like 4?
Hey. Yeah, we had a formula here. The formula now has simplified everything. This formula. Since we are dealing in a binary system, then the first one is going to be a 2 to the power 0. Then the 1 is going to be, okay, let me repeat it.
I also have another method. Excuse me, sir. I have another method for number of rows specifically.
Can you say it up? Can you say it?
If you want to know the number of rows, it is 2 to the power n. N represents the number of switches or the number of gates within the circuit. For the case of the circuit, the n represents the number of switches. So for instance, in this switch, you have K1 and K2. That means 2 to the power n, 2 to the power 2, giving you 4 rows. The one that we had previously looked at had 3 switches, K1, K2, K3. That means 2 to the power 3, giving us 8.
Have you understood that? Yes, I think that also makes a lot of sense. So our formula is here where n represents the number of switches. So if there are 2 switches, that means we shall have 4 possibilities. If there are 3 switches, that means it will be 2 power 3. There will be 8 possibilities. If there are 4 switches, there will be how many possibilities? If there are 4 switches, there are how many possibilities? 2 power 4. 2 power 4 is a what, by the way? A 16 or 32. I think it started to not so.
Yes, it started.
So if there are 4 switches, there are 32 possibilities, but 32 will be too much for you. The maximum will always be 3 switches. But if there are 2, someone gave us a very good formula, and he said that for you to easily fill in this table, this is a 2 power 0, and this is a 2 power 1. A 2 power 0 means that the pattern will repeat after 1 digit. A 2 power 1, you get a 2, meaning that the pattern repeats after 2 digits. For example, if I begin with 0, it will repeat after, then we shall have 1, 1. So on the other hand, 2 power 0 is a 1, meaning that after 1 digit, the pattern repeats 0, 1, 0, 1, like that. Now, remember we got this one from the circuit. Now I want to use the OR symbol. The OR symbol gives us an addition. So if we simply add, what do we come up with? 0 plus 0, you get 0. 0 plus 1, you get 1. 1 plus 0, you get 1. And 1 plus 1, you get 1. Now, there's something that I wanted to talk about after explaining this. You see how we say 1 plus 1 is a 1. Now, this is a special kind of mathematics, because in normal mathematics, 1 plus 1 is a what? 1 plus 1 is a 2. But remember, we are dealing with binary base. Binary base is where all the digits are either 0 or 1. So this kind of algebra was first studied and implemented by a person called Bully. That's why it is called Boolean algebra. So the addition, that when I add 0 plus 0, I get 0. 0 plus 1, I get 1. 1 plus 0, I get 1. 1 plus 1, I get 1. That kind of algebra is called Boolean algebra. Is that okay? So the Boolean equation says that their equation is not one equation. For OR gate, that is OR gate. For OR gate, if I have K1 plus K2, or if I have K1 and K2, if I have K1 and K2, then the result is going to be K1 plus K2. We say K1 or K2, which is the same as K1 plus K2. Is that okay?
Yes. Bless you, you have something to say.
Excuse me, teacher. I'm still lost where you mentioned that 3 gates and it's an AND gate. I thought that with an AND gate, they have to be like 2 gates. When they both turn out to be correct, like true, they give you like the gate. Sorry, the result is closed. So I am lost with the 3 switches.
Oh, okay. Okay, we shall have an example where, of course, with the 3 switches, it is always better that we first deal with the first 2, and then we combine we put in the third one. But we shall see. We shall have an example. Is that okay?
Okay, sir.
Yes.
Okay. We shall have an example. So another kind of gate that I don't want us to miss out is called the NOT gate. The NOT what?
Gate.
NOT, like you hear the word NOT. NOT. You go, I will not.
So, excuse me, teacher. I just have a question about Boolean algebra. Okay, yeah, I thought Boolean algebra is more of true, false. Is it that?
More of true?
Or false within the truth table? Okay, so help explain what Boolean algebra is.
Okay. So you remember if we have our gates, say, A and B, and then let's say we are having A and what? And B. Which gate is this now? The AND gate. This is A and B, not so? So in the truth table, our possibility is 0, 0, 1, 1. We can have 0, 1, 0, 1. So the result is going to be A and what? Now, from the truth table, how do I get the last column? The last column, I'll do some simple mathematics. That for me to get the results in the third column, I'll have to multiply 0 times 0, I get a 0. 0 times 1, I get a 1. So this kind of computation is what we call the Boolean algebra. Algebra simply means dealing with numbers or unknowns. It is not, the word on its own is not so much complicated. This was supposed to be a 0, 0, and a 1. That is for the AND gate. Is that okay? Is that okay? Okay. The one who asked, I don't know if we have answered her, but actually Boolean algebra, that the multiplication for the and then the addition for the or is one that constitutes the Boolean what? Algebra. Is that okay?
Yes.
So, unless if there is any question or supplement, but we can go to something else now. We are looking at the NOT gate. The NOT is where sometimes it is called an inverter. I'll just give an example. You know how you, just giving an example, how you press a switch in the position where you expect it to be on. Now the bulb is off. But when you expect the bulb to be on, depending on the position of the switch, now the bulb is what? The bulb is on. So in other words, this switch gives the opposite of what is expected. Gives the opposite of what is expected. So such arrangement is called, by the way, I didn't tell you that the physical switches that we use in our homes, they just give us a picture. But the true or the actual switches, in most cases, we are talking about transistors, switches in the motherboards. So because we know that one of the advantages over these physical switches is that they can switch on and off at a very higher frequencies. That comes with many advantages over these physical switches that we use. However, even with the physical switches, we get the insight of what the on and off means. Is that okay? So the NOT gate, or sometimes we call it an inverter, it inverts. You expect the input to be A, then the output comes out to be the opposite. That's how we indicate it. It inverts altogether.
Yes.
So inverting means that if I have my table, and then this is the input, and then this is the output, if the input is 0, then the output is a 1. And if the input is a 1, the output is 0. In other words, it gives the opposite of the input. You get that?
Yes.
So we can apply this arrangement. We can combine this kind of gate with any of the other two gates that we looked at. We looked at the and we looked at the or. Is that okay? So we can combine, for example, the not gate and the and the combination comes with a very good name, NAND. Not and gives you NAND. The N in this case stands for not. In other words, after computing and, then you invert. The result you get in and, you get the opposite of that result. For example, if I have my two inputs, A and B, and then I have A and, this is the AND gate now, A and B. That okay? So let's say this is 0, 0, 1, 1, and then this is 0, 1, 0, 1. A and B is going to be multiply 0, 0, 0, 1. Then, if I'm looking for the NAND, A, now I have combined A NAND B. The N in this expression, inverts the result of AND. So what is going to be here? If this was 0, then this becomes 1, 1, 1, and a 0. Do we get that?
Yes.
Others, do we get that? Yes, Blessing.
Blessing, unmute yourself.
So why not 0?
Where?
The O and then don't we get 0? Why do we have to write 1?
Who can answer her?
Aliyah.
Mm-hmm.
Aliyah, unmute yourself.
So I think you get 1 because NAND is the opposite of AND. So originally the answer is supposed to be 0, but since there's a not gate on it, it becomes the opposite. And instead of putting on a 0, you put a 1.
And this is the symbol for NAND. This is A, this is B, this is A, NAND B. So if you want to combine the two symbols for AND not, then you come up with that one. Is that okay?
Then Sekaita Emmanuel has something to say. Yes, Sekaita.
I wanted to ask. Hello?
Yes.
Yeah. Like I wanted to ask the other method which the Ethiopia told us, I think, that we write we first write 2, 2, 2, and then we write the powers, and then we calculate. Does that method work even for AND gates, or it is specifically for the other first two?
The method works for the first two columns. It guides you. Yes? It simply guides you in getting how many entries we have, how many rows do we have for the first two columns. It just guides you.
Then H still has.
Yes? Okay, friends, let's continue. We have a lot to look at. We have not looked at potential dividers and some other applications. Okay. So this is for the NAND gate. How about let's now see what happens if I combine NOT and NOT and OR. NOT and OR gives a very interesting result. Who can guess? NOR. Not so. So, and how do we come up with that kind of this kind of gate? If I have two inputs, A and B, then I have A or B, then A nor B. The N in this equation, the N in this means it will invert the result of OR. If OR is 0 and you put N, it makes everything 1. If OR is 1 and then you put N, it makes everything the opposite. So let us see what happens now. 0, 0, 1, 1, 0, 1, 0, 1. Oh, O means addition. We said that. 0 plus 0, 0, 1, 1, 1. Is that okay? So what is going to be the result in the in the third column? Yes, Tricia. Yes? Okay. What is going to be the result? Where we have OR, and it is a 0, NOR inverts it to a 1. If it is a 1, this becomes a 0, and a 0. And what is the symbol for NOR? This is A and that is B. You know, the circle comes from for the NOT gate. Is that okay? Okay, so let us go to something else. There is some other one. It's called XOR. Exclusive OR. So what does exclusive OR does? So if this is A, B, and then we have exclusive, okay. Let me say this is A exclusive OR. It is 0, 0, 1, 1, 0, 1, 0, 1. So what this one does, are we there? Are we there?
Yes, teacher. Hello.
Okay, so what this one does is that it outputs a 1 for as long as the inputs are different, and outputs a 0 for as long as the inputs are the same. You see that? Outputs a 0 for as long as what? Yes, please. Then there is another one that is called the XNOR. XNOR is the opposite of that one. If you have A and B, I wish we can have some time to have day life examples of this. This is A, XNOR B. I hope people are writing somewhere. So still, if we have 0, 0, 1, 1, 0, 1, 0, 1. So XNOR outputs 1 if the inputs are the same, and outputs is 0 if the inputs are different. Let me give just 1 minute for you to comprehend that. Is that okay? Okay, so let us now have let us upgrade to the combination of these switches or of these gates. So number 1, we are going to come up with the tables where we combine 2 gates and we see the result that we come up with. For example, if you have 2 gates, the AND gate and another AND gate. Let's say okay. We have this and we have that. This is it. We have AP. This is X, Y. And let's see PQ. And then this one is the final result. Is that okay? Now, what do you notice? That the first 2 gates, M and N, are AND gates. And then this H, it is an OR gate. And then we are asked to come up with a truth table. Come up with a truth table. So let's first deal with the inputs. Are we there? Let me first use this one. Okay, so we have the AND gate, we have the NOT gate, and then on the other side we have the NOR gate. So we have combined all the 3 at once. So I want us to figure out the results that we are going to have in our truth table. So this is A, and then this is B. Then we have P, we have Q, and then we have R. So we begin with the A. What are the possibilities? 0, 0, 1, 1. B is going to be 0, 1, 0, 1. Now, we have a possibility, a B that branches into the NOT gate. Branches into the NOT gate. So, but before that one, we can first work out to P. What is going to be P? P is the result of the AND gate, which is 0 times 0, we get 0. Here we get 0. Here we get 0, and we get 1. Now, what is going to be Q? You see that Q branches off from the input B. Q branches off from the input B, meaning that Q inverts the input from B. If B is a 0, Q is a 1. If B is a 1, Q is a 0. If B is a 0, Q is a 1. And if B is a 1, Q is a 0. So can someone work out R? R combines P and Q. And it combines P and Q in an OR gate. OR means we simply add. So that P plus Q to get R, 0 plus 1. So this will be a 1, a 0, a 1, and a 1. So our final result, R, would be that one. So I want to give 2 minutes. And in the 2 minutes, I request someone to re-explain on my behalf so that people can understand it better. Yes? Any volunteer? Yes, the hands, if the hand is re-explaining, please go ahead. No one? Oh, we have not understood anything. Yes? Nsubuga, what happened? You are helping me with those one too. Okay, head up 2024. I think I can unmute this one to say something. Okay, say something. Those who are putting up the hand, are you putting your suggestions in the chat? I check.
Chris is saying he can explain.
If you can, please. If you can be unmuted, go ahead.
You can unmute Chris or Alia, one of them. They have typed here.
I think they are trying. I'm also trying to unmute. Does it mean I first mute others? I don't know.
Chris,
okay.
Yes. Good afternoon, sir.
Good afternoon.
Yes. The results. First of all, the first gate is a what? Is an AND gate. And we know that for an AND gate to work, both the switches must be what? Completed or closed. So you say that if both the switches are open, P will be 0, or there will not be any current flowing. Then same to the second one, 0, 1, there will be no current. Same to that one, but when both A and B are closed, there will be current, because an AND gate can let out current when the switches, both the switches are complete or closed. Now, the Q is connected on what? On switch B. So, and the Q is a what? Is a NOT gate. The NOT gate works, it inverts the what? The input. The input, for example, B is open, it will invert it, and the what? The output will be 1. Then when B is closed, or when B is closed or it has 1, it will invert it to 0. Then when it is open, it will invert it to 1. And when it is closed, it will invert it to what? To 0. Because that is the working principle of an inverter or a NOT gate. Now, the result we get when we combine P and Q is, because this is the what? An OR gate. And an OR gate work, it works on a principle that one of the what? One of the switches must be what? Closed. So when P is open and Q is closed, there will be current flowing, because the OR gate is arranged in what? In parallel. So when P is open and Q is open, there will be no current flowing. So the result will be 0. Same to when P is open and Q is closed, there will be current flowing. And when P is closed and Q is open, there will be current flowing. That's it.
Okay. Thank you so much. People, have we picked something? Okay, I hope we have picked something now. I will. We are going to have another example on this one, but I'll just slide through to show you what we have covered so far. Someone might ask, ever since we began, we are on the first page. We have looked at a lot of stuff. So the digital signal, I talked about that digital switches have a signal 0 and 1, or high and low, or true or false. We talked about that. I talked about the binary numbers, the Boolean algebra. We talked about the OR operation, where we add to get the result. We've talked about the AND operation that gives us the AND gate, where we multiply to get the result. We talked about the NOT gate, where the gate inverts the input, and we have something like the table is given. So we have some examples here, the truth tables of the OR and the AND. Then I talked about the NOT gate. We talked about the NOR gate, NOR, which combines NOT and OR. Then we talked about the XOR, and XOR. What did I say about XOR? I said it outputs 0 when the inputs are both 0 and outputs 1 when the inputs are opposite. So when the inputs are opposite, it outputs 1. But when the inputs are the same, it outputs 0. That's the XOR. And then XNOR does the opposite of XOR. XNOR outputs 1 when the inputs are the same. If you have 0, 0, it outputs 1. If you have, maybe I had not given the symbol for XOR and XNOR. Okay, symbol for XOR and XNOR. XOR, it is that one. This one. And then of course, this one, someone is going to say about this B looks weird. You can have it as a straight line, not necessarily a bending. Here I was trying to draw the diagrams using coding. Okay. And then for XNOR, which we have looked at, the symbol is still that one. The computation of XNOR, I said it. I say that where the inputs are the same, for example, 0, 0, the output is a 1. If the inputs are 1, 1, the output is still a 1. But if the inputs are opposite, then the output is a 0. Yeah, the scenario I'm going to, after this one, I'm going to give a scenario-based question. Is that okay? Yeah, so yeah, that one. So now the scenario-based question, let me just formulate one right now. Listen carefully. For those who have where to write, you can write. The question says that a home has two doors. A home has 2 doors. Are you writing? Okay, let me write it somewhere. I'm formulating one, and we are saying that a home, okay, let me just type. Okay, let me look for where is typing. Our home has 2 doors, comma, the front door and the back door. The home security system works on the following conditions. works on the following what? Conditions. The alarm is on only if both doors are open. Only if both doors are. The alarm is, let me put it this way, the alarm is off only if both doors are closed. And we are saying that using the logic circuit diagram generate a truth table for the operation of this alarm system. A home has two doors, the front door and the back door. The home security system works. The home security system works on the following conditions. The alarm is off only if the following condition. The alarm is off. The alarm is off. The alarm is on. The alarm is on only if both doors are The alarm is off only if both doors are closed. Using the logic circuit diagram, generate a truth table for the operation of this alarm system. Okay. Now, just read through and someone tell me what this scenario is asking us to draw. Which kind of logic gate are we going to draw and why? Yes? Yes, please.
Let me unmute this. I am at you can unmute yourself.
Yes, good evening, teacher.
Good evening.
So I think it's an AND gate.
Why?
This is because the alarm will go on if both doors are open.
Here we are saying that the alarm is off only if both doors are closed. What does that mean? That if one of the door is open or if both doors are open, the alarm will be on.
Yes.
So which gate is that?
An AND gate.
Thank you for trying. Another person?
Teacher? Yeah, I think it's an OR gate.
Why?
Because they say that the alarm is off only if both doors are closed. So me, I let closed to mean 0 and off means 0 as well. That means that if like that means that it can be on for as long as even only maybe if one door is open or that. So that means it's an OR gate.
Okay. Let's say let's try to figure it out. Let's say we have D1, the door has D1 and then door has D2. And then we are told that, this is the result, we are told that the alarm is off only if both doors are closed. So meaning that there are two doors, so how many possibilities? 0, 1, 0, 1. So the alarm is off only if both doors are so if we consider the OR, if we consider the OR gate, then it is going to be 0, 1, 0. Am I right? No. It's going to be 1,
1, 1, 1.
1, 1, not so.
Mm.
So this is if we are to consider the OR. And if we are to consider the OR, does it bring out the message in the question? The result, now this one, let's call it the alarm. The alarm. So here we are seeing that the alarm is off only when both doors are open, and it is on for the rest. So this one does not work out. So what happens if it is and?
And will come out.
D1 and D2. So and will give us what? 0, 0, 0, and a 1.
1.
Yeah, so we say that for as long as the alarm will be on, now this means that we define 1 as on, then 0 as off. So the alarm will be on for as long as both doors are
open.
Are you sure?
Hey, teacher.
If both, because 1 represents closed, then 0 represents open. You see? Okay. So now let me tell you, I hope you wrote the question somewhere. So the interpretation is like this now. We shall have our two doors, D1, D2, then A and B. Let me first think. This is D1 and D2. Hope you wrote the question somewhere. We shall refer to it. 0, 0, 1, 1. This is 0, 1, 0, 1. So this is going to be, if it is and, it is going to be 0, 0, 0, 1. Not so? So yes. What am I going to do? What I'm going to do is that I will subject this gate to a NOT gate to be D1 NAND. NAND D2. If I subject it to a NOT gate, it will invert these zeros into a 1, 1, 1, and a 0. So that means that the alarm will be off only if both doors are what? So we see that when both doors are 0, 0, when both are open, we have a 1. The alarm will be on. When 1 is open, we have a 1. The alarm will be on. When 1 is closed, and the other one open, we have a 1. But when both are closed, we have a 0. So the alarm will be off. So the logic diagram for that is going to be a NAND. Then the output is A, NAND B. I just want one person to explain it better than me.
Teacher? But the OR gate gives us the same result.
The OR gate gives us the same what?
The same result. Like we should have 1, 1, 1, 0.
Oh, then those are two possibilities, which is okay. Is that fine? Those are two possibilities, which is fine. Okay. I don't know if time allows us to go through this one. What do you think?
Yes.
Have you people understood this? At least we've just looked at one practical, one day life application.
Yeah, these ones with the hands, maybe they have the questions. We may allow them. Yes, Bless, you can unmute and ask your questions.
Teacher, me, I am now confused again. The question says that if both doors are open, the alarm will sound. And if they are both closed, the alarm will be off. I think that doesn't answer that with the and, the NAND. It answers with the and.
It answers with a?
With an and, the and gate.
Now, who can respond to her? Because when of course, we began with the AND gate. We began with the AND gate, and the result was 0, 0. Here we are taking 0 to be, unless if we redefine that let 0 be off and let 0 be on and 1 be off. Do you get my point?
Yeah, me, I'm confused. No.
If we redefine and we say let 0 be off, let 0 be on and 1 be off, then you would stop at this point. Okay. Okay, but we have a basis. I hope when you go back, they will throw more insight on this. Yeah? I just wanted to take us through just a few things before we wind up. But at least you have a basis. Then we can just work out this simple one, because I'm responding to a question. One girl asked a question, which I promised that I'm going to give a clear explanation. Yeah.
Okay,
let me look for where there is space. So this girl asked a question for the 3 inputs, and supposing we have and we have a not, they both enter into an OR gate and then subjected to a not. What is the result? So this is 1, 2, 3. How many inputs are those? How many inputs are those ones? So we can call this one P, we can call this one Q, R, and then we can call our final output, we can call it S. So these are 3 inputs. Someone gave us a formula. If the inputs are 3, then the result is going to be 8 possibilities, yeah? So we have A, B, and a C. So what are the possibilities? We gave ourselves a formula. This is, we begin with the repeating after 4. This is 1, 1, 1, 1. Then the second one, they repeat after 2, 0, 0, 1, 1. 0, 0, 1, 1. And the last one, they repeat after 1, 0, 1, 0, 1, 0, 1, 0, 1. Now, now we subject these inputs to the logic circuit diagram. We first deal with AB. AB gives us P. It is an AND gate. We shall multiply A times B, 0, 0, 1 times 0. You tell me in case I make a mistake. Am I right? How about to C? How about to Q? Q inverts the input C. If C is a 0, Q is a 1. If C is a 1, Q is a 0. If C is a 0, a 1, like that. Now, how about R? R is as a result of the OR gate. Or I look for P and Q. Where is P and Q? P and Q I add. So 0 plus 1, I get 1, 0, 1, 0, 1, 0, 1, 0. And how about S? S is an inverter. It inverts the input R. So this is a 0, a 1, a 0, a 1, a 0, a 1, a 0, a 1.
Mr. John.
Yes?
Here P and Q, the last column here, it is a 1. On R,
Where?
the last on the row R, where we have R down. On
Down,
R, yes, down the last one.
The very last one, this one.
Yes.
Okay. PQ as in?
We are adding them. We have 1 plus 0. P is 1, then Q was 0. So it gives 1.
Hey. R gives a 1 here. We are adding. What else? How about in the last one? S.
Then S now, we are now inverting R. Which will be 0, 1, 0. 0, 1, 0, 1, 0, 1, 0,
0, 1.
0, 1.
0, 1.
0, 1. 0, 0.
0, 0, like that.
Yes.
Okay. So AB, when we multiplied, we got a 0 to get, we got a 0 AB to get Q. P was 0.
Yes.
And then Q was a 1. Okay, I think that is it. That is it. So, friends, any question? Uh-huh.
We have this ones with the questions. Winifred, you may unmute yourself.
Master, I'm just asking for if we can cover potential divide today.
Okay. Okay, let me just use some 5 minutes. We go through the potential divider. We may not have any other time, yet this is an opportunity. So, potential divider is an arrangement of two resistors, for example, when they are arranged in what? When they are arranged in series. So because we don't have time, I will not derive the formula, but I will just state it. If this is R1 and this is R2, and this is the supply voltage or the input voltage, if I want the voltage across R1, let me call it V1. Sometimes they call it the output voltage. If I want that voltage V1, then I will say it is the total voltage times R1 out of R1 plus R2. Out of R1 plus R2. So the formula is very simple, but I will not take us through the derivation. So for now, you can simply state it that way. For example, if our V is 6 voltage and R1 is 2 ohms and R2 is 4 ohms, what is going to be the voltage across R1? The total voltage times R1 is 2 out of R1 plus R2. That is 2 plus 4. So we shall get 6 times 2 over 6. Of course, this can reduce. So V1 becomes 2 volts. Is that okay? Is that okay? Now, supposing I instead put my voltmeter, instead of putting it at R1, now I want the voltmeter to read the voltage at R2. Still, the formula to get V2 will be the total voltage times. So where the voltmeter is what acts as my numerator of the resistance, R1 plus R2. So V2 becomes 6 times, what is R2? R2 was what? 4 out of 4 out of what? 2 plus 4. So V2 becomes 6 times 4 over 6. And of course, when you reduce, V2 becomes 4 volts. So do you realize that V1 plus V2, V1 we got 2, V2 was 4. So when you add 2 plus 4, you come up with the total voltage. Okay. So, so that is the potential divider. Its simple application is that it always gives the fraction of the voltage in any series arrangement. How is it applied in daily life? When we are tuning, for example, when we are tuning volume, every time you tune or change, you increase on the volume, you are adjusting the voltage. You're adjusting the what? The voltage. Sometimes we simply have it as this. If these are your two resistors, let's say this is the V input. That is the total voltage. Then you want the voltage across maybe one of the resistors. We call it V out. If this is 2 ohm and this is 1 ohm, supposing the voltage input or the supply voltage is 10, or let's see, any voltage, I can say 9 volts. What is the voltage out? It depends on which resistor you have connected across. So the V out is going to be the total voltage in times 1 ohm out of the sum, 1 plus 2. So the V in is given as 9 times 1 out of 3. So this can be, the V out for this case is going to be 3 volts. Is that okay? Okay. I beg to stop here. Is that okay?
Teacher.
Yes?
I have a question. Try going to send the work on what you've explained to us in the WhatsApp group. The work on
it is already there.
Yeah, but I don't have the work.
It is already there, but I'll ask Mr. Kaziba to resend.
Okay, Chair, thanks.
Okay, I hope people have picked something. So when you go to school, you encourage, not encourage, you can request teachers to give more application, daily life application. We have not seen a lot of them yet. I had more. Some are very complicated. I couldn't simply bring them in like that. Okay, the recording is going to be shared by Mr. Kaziba, don't worry.
May you please send, okay, the recording? Because some of us at the end of the lesson were off.
Mr. Kaziba is going to share the recording. It is going to be there on YouTube.
Okay, thank you.
Okay, have a blessed evening. In case of any question, I think I can just share. No, but you don't need a number. You'll contact Mr. Kaziba in case of anything. Is it okay?
Yes.
Okay, maybe to let you know, I'm a teacher, Gayaza High School. Physics. Where do they end the lesson from?
They may give us the closing prayer.
Closing prayer, please. Yes, please.
Let me unmute one to give us. Yes, Michael. You may unmute yourself and give us the closing prayer.
Dear Lord, we thank you for this lesson that you've given us. We thank you for our teachers. We thank you for the time that they have given us. We thank you for all that we have managed to learn. And we ask you to bless them abundantly for their time, their knowledge that they have shared with us, and also bless us as we've learned. May the knowledge that we've gained help us in the coming UNEB and in our daily lives. And we also request you in the next lessons, come and be with us, come and keep us. Where we're going, some are going to start the term next week, others soon. Come and guide us, because our goal is to succeed. We pray through Jesus Christ. Amen.
Amen. Okay, thank you so much. Okay, have a blessed evening.